Hey everybody, welcome back. This is section 10.10, the pKa method for expressing acid strength. So our goals in this section are to be able to express acid strength in terms of pKa, so calculate the pKa for an acid, and then to define the relationship between the Ka, the pKa, and acid strength. So the Ka, the acid ionization constant, is the equilibrium constant for the reaction of an acid with water. If we write out how to calculate Ka, it's the concentration of each of the products when an acid ionizes in water divided by each of the reactants. We go back to writing out our general equation for an acid, Ha plus H2O liquid makes H3O plus aqueous plus A minus aqueous. So it's the concentration of H3O plus times the concentration of A minus, those are our products, divided by the concentration of HA. And we don't include water because water is a pure liquid. So we've gone over how to calculate Ka earlier in chapter 10. So just like the concentration of hydronium ions can be converted into pH by taking the negative log, the Ka value for an acid can be converted into pKa by taking the negative log. And I mentioned in the pH section that when you see this P, it means take the negative log. So to find the pKa, you take the negative log of the Ka. So how does this relate to Ka, which we've already talked about, and percent ionization and acid strength? So for stronger acids, we have higher Ka values, meaning that more of the acid ionizes when it's put in water. Let's write out our general acid equation. Ha aqueous plus H2O liquid turns into H3O plus aqueous plus A minus aqueous. So this is the acid ionization equation when an acid ionizes to make H plus ions and A minus ions. The H plus ions bond with water. Water acts as the base to generate H3O plus, and then you have A minus left in solution. So stronger acids have higher Ka values, which means that we make a lot of the products. The reaction is pushed to the right, which means we have a higher percent ionization. More of HA is going to ionize into H plus and A minus, and every time we generate some H plus from ionization, it bonds with H2O to make H3O plus. When we calculate the pKa of something with a high Ka, the pKa is going to be smaller or lower. So because we're taking the negative log when we calculate pKas, the pKa value will be less when we have a higher Ka value. Just like with pH, when we have a higher concentration of hydronium ion, H3O plus, the pH value is lower because we're taking the negative log. For weaker acids, the lower the Ka, the weaker the acid, which means you have a lower percent ionization, less of this acid is going to ionize, which means you're going to generate less of each of these products, which means that when you take the negative log of this low Ka, you're going to have a higher pKa value. So higher pKa values arise from small Ka values, which means the acid does not dissociate easily in water, which means it's a weaker acid. So weak acids have high pKa values, right? Weak acids have high pKa values, and stronger acids are going to have lower pKa values. So it's the opposite if you're ranking things. When you're ranking by pKa, it goes in the opposite direction compared to Ka. And again, that's because pKa is the negative log of the Ka. So by taking the negative log, that's why a high Ka value results in a low pKa value. Just like a high hydronium ion concentration when you're finding the pH results in a low pH. So let's do a couple example problems. Let's calculate the pKa for hydrofluoric acid, given that the acid ionization constant, the Ka for this acid is 6.8 times 10 to the negative fourth. So we are given the Ka equals 6.8 times 10 to the negative fourth. We want to find pKa. We're going to use the equation for pKa directly. So pKa equals negative log of the Ka. So when we solve this, we can plug in our Ka value. So the negative log of 6.8 times 10 to the negative fourth is going to give us our pKa. This is one I can't do in my head, so I'm going to plug it in. Negative log of 6.8 times 10 to the negative 4. And I get a pKa of 3.1674 and so forth. And so because we were going from log function to the p function, the pKa, just like with pH, we're going to add 1 sig fig. So we had 2 sig figs here, which means our final answer here is going to have 3 sig figs. So we get 3.17 is the pKa. Let's do another one. Let's use the Ka or pKa values, depending which one's given, to be able to rank these acids from strongest to weakest. So let's say the strongest acid is going to be number 1 and the weakest acid is going to be number 4. So if we start with the first one in the list, phosphoric acid, the pKa is 2.12. And this is the pKa at which the first hydrogen comes off of phosphoric acid. If you recall from polyprotic acids, each time a hydrogen comes off, it comes off in its own step. And so a polyprotic acid will have multiple pKa values. A pKa value at the molecular level signifies the pH at which a proton is going to come off of an acid, to ionize off. So the first proton will ionize off of phosphoric acid at a pH of 2.12. That's the pKa value for that acid. Okay, so we have 2.12, 4.75, another pKa value for acetic acid. Formic acid, we're given the Ka value. So we're going to have to convert this to pKa so we can compare everything on a pKa basis. And then carbonic acid, we have a pKa of 6.37. So right now, before we figure out the pKa of formic acid, we have that phosphoric acid is the strongest, acetic acid is the second strongest, and carbonic acid is the third strongest. Again, ranking from strongest acid to weakest acid based on what we know so far. The lower the pKa, the stronger the acid. So let's find out the pKa of formic acid so we can figure out where it fits in this ranking. So pKa equals negative log of the Ka, so negative log of 1.77 times 10 to the negative fourth. And I get 3.75. And I'll add a sig fig, so 3.752. pKa equals 3.752. So now that we know the pKa's for each one, we can rank them completely in order, with number 1 being the strongest acid. So our strongest acid has the lowest pKa, so that's phosphoric acid, so that gets ranking number 1 for strongest. Our second strongest one has the next highest pKa, which would be formic acid, so that's number 2. Then acetic acid has a pKa of 4.75, so that's number 3. And then carbonic acid has a pKa of 6.37, so that would be number 4. So this is strongest, and this is weakest. So this was to really help you remember that the lower the pKa, the stronger the acid. pKa corresponds with pH, just like the lower the pH, the stronger the acid. It's the same with pKa. The lower the pKa, the stronger the acid. Okay, so we have another practice quiz on Kahoot. If you're interested in taking it, it's totally optional, but it's put up to help you prepare for the quiz and to hopefully have some fun and get to review this stuff a little bit. So you should be able to access it by clicking on this link. And then if you enter in the Kahoot ID that's in bold below, you'll be able to take the quiz on your own time. So do it as a way to, again, get some extra practice before taking our next quick quiz or before our next exam. If you have any issues with using this link, please be sure to reach out and email me so I can figure out if there's a way I can fix it, because I do want you to be able to have access to this. And it's the first time I'm trying it asynchronously instead of having everybody do the Kahoot at the same time. So if there's any difficulties, just let me know and I'll work on it. Okay, thanks. That's it for this section, and we'll pick up next time. See you later.